There's something hauntingly beautiful about a star that shouldn't exist. Picture this: you're staring up at the night sky, tracing the familiar constellations, when suddenly your eyes lock onto a flickering light that doesn't behave like anything else around it. It pulses erratically, vanishes for years, or maybe even moves in ways that defy every law of physics we've ever written. This isn't science fiction. These are stellar anomalies, cosmic rebels that challenge everything we think we know about the universe. And today, we're embarking on a journey to uncover 28 of the most mind-bending, inexplicable phenomena scattered across the cosmos. From black holes that roam like interstellar nomads to stars that simply disappear without a trace, these are the mysteries that keep astronomers awake at night, scratching their heads and rewriting textbooks. What makes these anomalies so captivating isn't just their strangeness, it's what they reveal about the gaps in our understanding. For centuries, we've mapped the heavens, believing we've decoded its rules, only for the universe to throw us another curveball. Take, for instance, the star that dims unpredictably, sparking wild theories about alien megastructures, or the black hole that shouldn't be where it is, defying the very fabric of spacetime. These aren't just quirks, they're cosmic breadcrumbs hinting at forces and dimensions we've yet to discover. And that's the thrill of it all. Every anomaly is a doorway, a chance to peer into the unknown and ask what else is out there. This video is your invitation to step through that doorway. We'll unravel the science behind these celestial oddities, exploring the leading theories and the tantalizing questions that remain. Some of these mysteries may never be solved in our lifetime, but that's the beauty of the cosmos. It refuses to be fully known. So whether you're a seasoned stargazer or someone who simply loves a good cosmic whodunit, prepare to have your curiosity ignited. By the time we're done, you'll never look at the night sky the same way again. The universe is stranger, wilder, and more wondrous than we've ever imagined, and it's time to dive in. Let's start with one of the most baffling cosmic puzzles of the last decade: Tabby's star, a flickering enigma that refuses to play by the rules. Officially known as KIC 8462852, this unassuming star in the constellation Cygnus behaves like nothing else we've ever seen. Most stars dim in predictable, rhythmic patterns like clockwork, but Tabby's star, it plunges into darkness at random, sometimes fading by up to 22% before snapping back to brightness, as if someone's toying with a celestial dimmer switch. When astronomers first spotted this erratic behavior in 2015, the internet erupted with wild speculation. Could this be evidence of an alien megastructure like a Dyson sphere, a hypothetical shell built by an advanced civilization to harness a star's energy? It's a tantalizing idea, but science demands more grounded explanations. Some researchers point to swarms of comets, massive enough to blot out the star's light as they pass. Others suggest interstellar dust or even a rogue planet with rings dwarfing Saturn's. Yet none of these theories fully account for the star's extreme, irregular dimming. What makes Tabby's star so fascinating isn't just its strangeness, it's how it exposes the limits of our knowledge. Here's a stellar object behaving in ways no model predicted, forcing us to reconsider what's possible. Could it be a natural phenomenon we've never witnessed before, or does it hint at something even more extraordinary? Every flicker of this star is a reminder: the universe is far weirder than we've dared to imagine. And that's just the beginning of our journey through the cosmos' greatest mysteries. If Tabby's star left you questioning the rules of the cosmos, brace yourself, because the universe has another curveball to throw. Imagine a supermassive black hole, an object so heavy it could anchor an entire galaxy, suddenly breaking free and barreling through space like a cosmic wrecking ball. That's exactly what astronomers witnessed when they spotted a black hole weighing as much as 20 million suns racing across the universe at staggering speeds, dragging a 200,000 light-year long trail of newborn stars behind it. This isn't just unusual, it's downright unthinkable. Supermassive black holes are supposed to sit quietly at the centers of galaxies, not go rogue. So how did this one escape? The answer lies in chaos, violent, galaxy-shattering chaos. Picture two galaxies colliding, their supermassive black holes spiraling toward each other until they merge. But sometimes, if a third black hole gets involved, the gravitational dance can fling one of them outward like a slingshot. That's likely what happened here, an intergalactic game of billiards with the ultimate high-stakes outcome. The Runaway black hole's trail of young stars is another puzzle. As it plows through clouds of gas, the shockwaves compress the material, igniting star formation in its wake. It's a cosmic paradox, destruction giving birth to creation. What makes this discovery so groundbreaking isn't just the black hole's speed, it's what it reveals about the hidden forces shaping our universe. Galactic collisions might be far more chaotic than we realized, with black holes ejected into the void like interstellar outcasts. Could there be more of these rogue giants drifting unseen? And if so, what does that mean for the structure of the cosmos? Every time we think we've mapped the heavens, the universe reminds us there's always another layer to unravel. This Runaway black hole isn't just an anomaly. It's a glimpse into the violent, dynamic processes that sculpt the galaxies around us. And it's proof that even the most massive objects in existence are still at the mercy of forces we're only beginning to understand. Now imagine an invisible hand tugging at the fabric of the universe itself, pulling entire galaxies, including our own Milky Way, towards something we can't even see. That's the Great Attractor, one of the cosmos' most perplexing mysteries. Hidden behind thick clouds of dust and stars in the Milky Way's plane, this gravitational behemoth exerts a force so powerful, it's dragging thousands of galaxies toward it at speeds exceeding 2 million kilometers per hour. Yet, despite decades of research, we still don't know what it actually is. The strangest part, when astronomers first noticed galaxies moving toward this unseen force in the 1970s, they expected to find a massive cluster of visible matter, a supercluster of galaxies perhaps. But when they trained their telescopes on the region, they found almost nothing. The Great Attractor's pull couldn't be explained by the ordinary matter we could detect. So what's causing it? One leading theory points to dark matter, an invisible, mysterious substance that makes up about 85% of the universe's mass. If there's a dense knot of dark matter lurking there, it could explain the gravitational tug, but even that doesn't fully account for the sheer scale of the phenomenon. Then there's the wilder possibility. Could the Great Attractor be something even more exotic? Some theorists have floated the idea of a cosmic flaw in space-time, a remnant from the early universe, or even a portal to another dimension. Others suggest it might be the gravitational echo of a long-forgotten collision between universes in the multiverse. While these ideas sound like science fiction, they highlight just how little we truly understand about the forces shaping our cosmic neighborhood. What makes the Great Attractor so unnerving is its proximity. It's not some distant quirk of the universe, it's close, cosmically speaking, just 250 million light-years away. That means whatever's lurking there is influencing the fate of our local galactic group, including Andromeda and the Milky Way. And yet, because it's obscured by our own galaxy's dust, studying it is like trying to read a book through a fogged-up window. New instruments like radio telescopes and infrared observatories are finally piercing that veil, but every answer seems to reveal deeper questions. The Great Attractor isn't just a scientific puzzle, it's a humbling reminder of how much of the universe remains hidden from us. Even as we map the cosmos with unprecedented precision, there are forces at work beyond our comprehension, pulling strings we can't yet see. Whether it's dark matter, a cosmic anomaly, or something beyond our current physics, one thing is certain: the universe loves to keep us guessing, and that's what makes the hunt so thrilling. Every time we think we've grasped the rules, the cosmos whispers back, "You've only just begun." If the great attractor feels like an unseen force pulling the cosmos into its grasp, then the Boötes void is its polar opposite, a staggering absence, a cosmic desert so vast it defies comprehension. Stretching 330 million light-years across, this enormous region of space is almost entirely empty, a gaping hole in the universe's otherwise crowded tapestry. Astronomers call it the Great Nothing, and for good reason. Where most patches of the cosmos teem with galaxies, the Boötes void holds just a handful, scattered like lost travelers in an endless wasteland. How could something this vast, this empty exist? The universe, after all, is supposed to be clumpy. Matter gathers into galaxies, which cluster into groups, which form sprawling superclusters, all woven together by filaments of dark matter. But the Boötes void throws a wrench into that model. It's not just a small gap, it's a chasm so gigantic that if the Milky Way sat at its center, we wouldn't have known other galaxies existed until the 1960s. That's how sparse it is. Theories about its origin range from the unsettling to the downright bizarre. One possibility is that it's the aftermath of a cosmic collision, a region where two immense bubbles of space-time brushed against each other in the early universe, pushing matter aside like a boat's wake. Another idea suggests it's a relic of an ancient phase transition, a flaw in the fabric of reality left over from the universe's infancy. Or maybe, just maybe, it's the imprint of something even stranger, a shadow of higher dimensions or a scar from a long-vanished parallel universe. What makes the Boötes void so unnerving isn't just its size, it's the implication that our understanding of cosmic structure might be incomplete. Voids exist elsewhere, but none this extreme. If such a colossal emptiness can form naturally, what does that say about the forces shaping the cosmos? Are we missing a fundamental piece of the puzzle? Every time we peer into this abyss, it seems to whisper back with more questions than answers. Yet amid the mystery, there's a strange beauty to the void. Those few galaxies trapped inside it are like cosmic castaways, isolated in a sea of nothingness. Some show signs of stunted evolution, their star formation stifled by the lack of neighbors to collide and interact with. It's a reminder that emptiness isn't passive, it shapes the fate of everything within it. The Boötes void forces us to confront the limits of our knowledge. Is it a statistical fluke, a rare but natural phenomenon? Or is it evidence of something deeper, a wrinkle in the laws of physics we've yet to uncover? One thing's certain, in a universe that's supposed to be brimming with matter, the Great Nothing stands as one of the most haunting enigmas of all, a silent, yawning expanse that refuses to be ignored. Fast radio bursts are like the universe's cryptic Morse code, blasts of energy so intense they outshine entire galaxies, yet so brief they vanish before we can fully grasp them. Lasting mere milliseconds, these cosmic flashes erupt without warning, flinging beams of radio waves across billions of light-years. Some burst once and never return, while others pulse in strange, repeating rhythms, as if the cosmos is teasing us with a riddle we can't quite crack. The first fast radio burst was detected in 2007, buried in archival data from a radio telescope in Australia. At first, astronomers dismissed it as an anomaly, maybe a glitch in the equipment or a nearby satellite acting up. But then more appeared, each one arriving from deep space, carrying energy equivalent to 500 million suns packed into a fraction of a second. The sheer power was staggering, but the real mystery was their origin. What could possibly unleash such violent, fleeting bursts? One leading suspect is Magnetar's highly magnetized neutron stars that occasionally unleash apocalyptic tantrums. When their crusts crack under immense strain, they might release titanic flares capable of producing these bursts. Another theory points to colliding neutron stars, their violent mergers sending shockwaves through the fabric of spacetime. But then there are the repeaters FRBs that flash over and over, sometimes in predictable patterns, defying explanations tied to one-time cataclysms. This unpredictability has sparked wilder speculation. Could these bursts be artificial? Some have dared to wonder if they're signatures of advanced civilizations, perhaps interstellar beacons, or even the byproduct of unimaginable energy harvesting technology. While the scientific community leans toward natural explanations, the mere possibility ignites our imagination. After all, history has taught us that the universe is often stranger than fiction. What makes FRBs so tantalizing isn't just their mystery, it's what they reveal about the cosmos. As these signals traverse the universe, they interact with the sparse matter between galaxies, leaving faint fingerprints that let astronomers map the invisible web of cosmic material. They're not just anomalies, they're tools helping us probe the darkest, most neglected corners of space. Yet with every new detection, the puzzle deepens. Some FRBs arrive with polarization patterns suggesting they've traveled through incredibly strong magnetic fields, while others seem to originate from regions devoid of obvious cosmic powerhouses. Are we dealing with multiple phenomena masquerading under one name, or is there a unifying explanation we've yet to uncover? One thing's certain, fast radio bursts are more than cosmic static. They're a reminder that the universe is alive with phenomena we're only beginning to detect, let alone understand. Every burst is a whisper from the void, challenging us to listen closer and to admit how much we still have left to learn. Rising from the heart of our galaxy like twin towers of energy, the Fermi bubbles are a testament to the Milky Way's violent past. These enormous structures, each stretching 25,000 light-years from the galactic center, glow faintly in gamma rays, a silent echo of some ancient cataclysm that shook the cosmos. Imagine standing on a planet within one of these bubbles. The night sky wouldn't just twinkle with stars, it would hum with invisible, high-energy light, a remnant of forces powerful enough to reshape the galaxy itself. When the Fermi Gamma Ray Space Telescope first detected these colossal formations in 2010, astronomers were stunned. The bubble's symmetry was uncanny, perfectly aligned with the galactic core, their edges razor-sharp, as if carved by some cosmic blade. Their energy signature was even more puzzling. Gamma rays, the most energetic form of light, typically come from extreme events like supernova or colliding neutron stars. But these bubbles were diffuse, uniform, and old, likely the result of an eruption that occurred millions of years ago. So what could have unleashed such a vast, lingering fury? One leading theory points to Sagittarius, a star, the supermassive black hole at our galaxy's center. Today, it's relatively quiet, but in the past, it might have gone through a feeding frenzy, devouring enormous amounts of gas and dust. As matter spiraled into the black hole, some could have been ejected in opposing jets at near light speed, inflating these giant bubbles like cosmic balloons. Another possibility, dark matter, the invisible stuff making up most of the universe's mass, might have annihilated itself in dense pockets near the core, unleashing energy in a slow, titanic burn. But here's where it gets even stranger. The bubbles aren't just relics, they're still evolving. Recent observations show faint, filament-like structures within them, suggesting ongoing turbulence. It's as if the galaxy's core exhaled once, and we're still watching the breath disperse. And then there's the mystery of their silence. An eruption powerful enough to create the Fermi bubbles should have left other traces, shockwaves in nearby gas clouds, distortions in the Milky Way's magnetic field. Yet, aside from the gamma rays, the evidence is eerily absent. What makes the Fermi bubbles so mesmerizing isn't just their scale, it's what they imply about our galaxy's hidden volatility. We think of the Milky Way as a stable, serene pinwheel of stars, but these bubbles reveal a history of chaos, a time when the heart of our cosmic home roared with unimaginable energy. They're a reminder that even the most familiar corners of the universe can hold explosive secrets, and that the quiet black hole we orbit today might just be biding its time. On August 15, 1977, a radio telescope in Ohio picked up a signal so extraordinary that the astronomer who discovered it scrawled, "Wow," in red ink on the printout, a moment of raw awe that would immortalize it in history. Lasting exactly 72 seconds, this narrowband radio burst blared at a frequency of 1,420 MHz, a quiet channel where human interference is rare and natural cosmic noise is almost non-existent. It came from the direction of the constellation Sagittarius, blazing 30 times louder than the background static of space before vanishing without a trace. Decades of follow-up scans found nothing, no repeat signal, no debris, no plausible explanation. To this day, the WOW signal remains one of the most tantalizing enigmas in the search for extraterrestrial intelligence. What made this signal so electrifying wasn't just its strength, it was its precision. Natural cosmic phenomena like pulsars or quasars don't emit such pure, narrowband radio waves. This was a laser-like beam, seemingly engineered to cut through the noise of the universe, exactly the kind of signal we'd expect from a civilization trying to announce its presence. Even the duration fits a hypothetical blueprint. 72 seconds matches the window Earth would be in a telescope's crosshairs as our planet's rotation swept the Ohio dish across a fixed point in space. It's as if someone out there timed it perfectly, yet science demands skepticism. Could there be a mundane explanation? Some argue it might have been a reflected signal, a human transmission bouncing off space debris or a passing comet. But no known comet was in that region at the time, and our own radio leaks tend to sprawl across frequencies, not hone in on one with surgical precision. Others suggest a glitch, but the Big Ear telescope's twin receivers caught the signal in sequence, ruling out equipment error. The more we scrutinize it, the more the WOW signal resists dismissal. Then there's the haunting question of silence. If this was a deliberate broadcast, why only once? Civilizations capable of such transmissions would likely repeat them, or at least leave technological traces. Unless, and here's the spine-tingling thought, it wasn't a message at all. Perhaps it was a fleeting accident, like a cosmic radar sweep or an alien power surge, a momentary blip in their infrastructure that we happened to catch. Or maybe the signal has repeated and we just weren't listening at the right time. The WOW signal's legacy isn't just about aliens, it's about how we confront the unknown. For a brief, glorious moment, the universe seemed to speak directly to us, only to retreat into silence. It taught us the importance of patience in the search for cosmic company, and the humility of realizing that even our most advanced tools might miss the next call. Whether it was a hello from the stars or a cosmic coincidence, one thing's certain: that solitary WOW on the printout captures the essence of astronomy itself. The thrill of the chase, the agony of the unanswered, and the unshakable hope that somewhere out there, someone might be listening too. There's something unsettling about watching galaxies move as if they're part of a cosmic parade, hundreds of massive clusters, all streaming in the same direction at breakneck speeds, like leaves caught in an invisible current. This isn't just random motion, it's a coordinated march toward something we can't see, something beyond the edge of the known universe. Astronomers call it dark flow, and it's one of the most provocative mysteries in modern cosmology. The discovery came from studying the cosmic microwave background, the afterglow of the Big Bang. Normally, this faint radiation should appear uniform, but when scientists mapped tiny temperature shifts caused by galaxy clusters moving through space, they noticed something bizarre. Over 700 clusters, each containing thousands of galaxies, were hurtling in the same direction at speeds exceeding 2 million miles per hour. Not just a few outliers, but a staggering fraction of the observable universe, all pulled toward a single point in the sky near the constellations Centaurus and Vela. What could possibly exert such a colossal gravitational tug? The unsettling answer: nothing inside our universe explains it. Dark flow suggests the presence of massive structures beyond the cosmic horizon, regions so distant their light hasn't had time to reach us in the nearly 14 billion years since the Big Bang. Imagine standing on a ship, seeing ocean currents curve toward an unseen continent just over the horizon. That's the scale of this mystery. Some theorists speculate these could be superclusters of unimaginable size, or even remnants of other universes brushing against our own in the multiverse. But here's where things get contentious. Not all scientists agree dark flow is real. Some argue it's a statistical fluke, an artifact of measurement errors or incomplete data. Others suggest it might be the gravitational echo of a long-ago collision between our universe and another, a cosmic fender bender that left everything slightly off-kilter. Yet the evidence persists, and newer observations continue to fuel the debate. What makes dark flow so revolutionary isn't just the potential existence of unseen structures. It's the implication that our universe might not be as isolated as we thought. If forces beyond our horizon can influence galaxies inside it, that rewrites the rules of cosmology. It hints at a cosmos far larger and more interconnected than we've dared to imagine, where the observable universe might just be a tiny bubble in an infinite ocean. And that's the heart of the mystery, not just where these galaxies are going, but what their journey tells us about the true scale of reality. Every time we think we've mapped the edges of existence, the universe reminds us there's always something further. Imagine a world where the ground beneath your feet isn't rock or ice but diamond. Not just scattered gems, but a planet-sized crystal glittering in the eternal night of space. That's the reality of PSRJ 1719-1438b, a planet so bizarre it defies every textbook definition of what a world should be. Discovered in 2009, orbiting a pulsar, a rapidly spinning stellar corpse, this cosmic jewel is unlike anything in our solar system. Its density suggests it's made almost entirely of crystallized carbon, compressed under unimaginable pressure into a structure that might resemble a diamond the size of a planet. How does something like this even form? The story begins with catastrophe. The pulsar it orbits was once a massive star that exploded in a supernova, stripping away its outer layers and leaving behind a dense, spinning core. Scientists believe the diamond planet might be the remnant of a white dwarf, a star that wasn't quite massive enough to explode on its own. When its companion star went supernova, the blast shockwaves could have ripped away the white dwarf's outer layers, leaving only its ultra-dense carbon core behind. Over eons, the carbon cooled and crystallized, turning into a celestial diamond under the pulsar's relentless glare. What makes this world so extraordinary isn't just its composition, it's what it reveals about the extremes of planetary evolution. Most planets form from the dusty leftovers of star birth, but this one is likely the skeleton of a dead star reshaped by violence. Its existence challenges our assumptions about what's possible. Could there be other diamond worlds out there, hidden in the gravitational embrace of pulsars or black holes? And if so, what strange geological processes, or should we say crystallographical processes, might unfold on their surfaces? Then there's the pulsar itself, a merciless timekeeper. This diamond planet orbits its neutron star host every 2 hours and 10 minutes, meaning a year there passes in less time than a typical movie. The gravitational forces at play are so intense that if you stood on its surface, assuming it even has a solid surface, the pulsar's radiation would vaporize you instantly. Yet, despite the hostility, this system is a gold mine, or rather, a diamond mine for scientists. The planet's extreme density helps astronomers test the limits of physics, probing how matter behaves under conditions we could never replicate on Earth. But here's the twist: this diamond might not be forever. Pulsars slowly lose energy over time, their spins winding down like cosmic clocks running out of battery. As this one dims, the fate of its glittering companion hangs in the balance. Will it eventually spiral into the pulsar, crushed into oblivion, or could it survive, a lone diamond adrift in the darkness long after its host has faded? The diamond planet isn't just a curiosity, it's a testament to the universe's boundless creativity. In the aftermath of stellar death, amid forces that shred atoms and warp space-time, nature still finds a way to craft something breathtaking. It's a reminder that even in the coldest reaches of space, there's beauty forged from chaos, waiting for us to uncover it. And who knows, maybe somewhere out there, another diamond world shimmers in the void, daring us to look closer. Most nebulae are cosmic masterpieces of chaos, turbulent swirls of gas and dust, sculpted by the violent winds of dying stars, but the red rectangle nebula breaks every rule. Floating 2,300 light-years away in the constellation Monoceros, this celestial oddity is a near-perfect geometric wonder, its crimson-lined structure so precise it looks almost engineered. At its heart, a dying star flings material outward, not in random bursts, but in two opposing cones that intersect to form an eerie, hourglass-shaped halo. The result, a vast, glowing rectangle that defies everything we know about how nebulae should behave. What makes this nebula so uncanny isn't just its shape, it's the mystery of how such symmetry survives in the universe's messy backyard. Most stellar ejecta get twisted by magnetic fields or blown into chaotic tendrils by radiation. But here, something, perhaps dense rings of dust around the central star, acts like a cosmic stencil, forcing the outflow into crisp, angular lines. Then there's the color. The red rectangle's rich burgundy glow comes from a rare form of carbon molecules stacked like microscopic snowflakes. These compounds, known as polycyclic aromatic hydrocarbons, usually form in the sooty aftermath of combustion. Finding them in space glowing like neon signs suggests chemistry far stranger than we've imagined, but the real puzzle lies deeper. The nebula's symmetry hints at forces we've never observed elsewhere. Some theorize the central star has a hidden companion, a second star whose gravity shepherds the ejected material into orderly paths. Others propose magnetic fields aligned with surgical precision, or even resonant vibrations in the dust itself, like sound waves freezing into visible form. Whatever the cause, the red rectangle stands as a cosmic rebellion against randomness, a reminder that nature sometimes trades chaos for geometry. And then there's the ticking clock. The star at the nebula's core is in its final act, shedding layers as it cools into a white dwarf. In a few thousand years, the stellar winds will fade, the dust will disperse, and this perfect rectangle will dissolve into the void. That fleetingness makes it all the more extraordinary, a fleeting masterpiece in a universe that usually favors entropy. The red rectangle doesn't just challenge our understanding of nebulae, it whispers of hidden laws, of symmetries we've yet to uncover. In its crimson lines, we see the universe's capacity for order not as an exception, but as a silent, persistent alternative to the chaos we've come to expect. It's a cosmic riddle wrapped in geometry, waiting for us to decode its secrets before it vanishes forever. The universe has a way of turning even the most intimate cosmic relationships into something sinister, and nowhere is that more evident than with the Black Widow pulsar. Picture this, a neutron star no larger than a city but weighing more than our sun, spinning at dizzying speeds, blasting its companion with lethal radiation. Over time, this deadly embrace strips the smaller star layer by layer, leaving behind a ghostly husk. It's a celestial predator with a taste for destruction, earning its name from the infamous spider that devours its mate. Discovered in 1988, the Black Widow pulsar, officially known as PSRB 1957+20, isn't just any neutron star. It rotates an astonishing 622 times per second, whipping its beams of radiation across space like a lighthouse from hell. Every pulse is a death sentence for its companion, a brown dwarf or lightweight star locked in orbit just 2 million kilometers away. That's closer than some planets are to their suns, bathing the victim in enough high-energy particles to vaporize entire atmospheres. What makes this system so chilling is the slow, inevitable unraveling of the doomed star. As the pulsar's radiation and gravitational tides tear into it, material gets ripped away, spiraling into a glowing disk around the neutron star before vanishing into oblivion. Some of this stolen matter fuels the pulsar's spin, making it even faster and deadlier, a self-sustaining cycle of cosmic cannibalism. But here's where it gets even stranger. Astronomers have spotted similar redback pulsars named after another deadly spider, where the companion star fights back, its own gases creating turbulent winds that occasionally eclipse the pulsar's signal. It's as if the prey isn't going quietly, lashing out in a final, desperate struggle. These systems are rare, but they hint at a broader truth. The universe's most violent dramas often play out in the quietest corners of space. The Black Widow pulsar isn't just a spectacle of destruction, it's a laboratory for extremes. The conditions here push the limits of physics, magnetic fields trillions of times stronger than Earth's, gravity so intense it warps light, and temperatures that defy imagination. Studying it helps us understand how matter behaves under forces we could never replicate on Earth. Yet beneath the science lies a darker poetry. This pulsar is a relic of stellar death, a reminder that even stars aren't guaranteed peaceful ends. Some are reborn as monsters, spinning faster as they feast on the remains of what was once their equal. And one day, long after the companion star is gone, the Black Widow will spin alone, a silent hunter waiting for the next cosmic dance to begin. Some galaxies age gracefully, their spiral arms brimming with newborn stars in a constant cycle of renewal. But NGC 1277 is a cosmic fossil, an ancient relic frozen in time. Nestled in the Perseus cluster 220 million light-years away, this cannibal galaxy hasn't formed new stars in over 10 billion years, preserving a snapshot of the early universe like a fly trapped in amber. What makes NGC 1277 so extraordinary isn't just its age, it's the eerie stillness. Most massive galaxies grow by merging with others, their collisions triggering bursts of star formation. Yet this one seems to have gorged itself early, swallowing smaller neighbors in a feeding frenzy that left it bloated and dormant. Today, it's a graveyard of aging red stars, their light tinged crimson by eons of cooling, with no young blue stars to break the monotony. Scientists call these red and dead galaxies, but NGC 1277 is an extreme case, a time capsule from an era when the universe was less than half its current age. The mystery deepens when you peer at its core. Most galaxies this massive host supermassive black holes proportional to their size, but NGC 1277's black hole is a behemoth, weighing 17 billion times the mass of our Sun, one of the heaviest ever recorded. That's like finding a whale's heart inside a goldfish. How did such a mismatched monster form? One theory suggests the galaxy's early cannibalism funneled vast amounts of gas into its center, feeding the black hole until it dwarfed everything around it. Another possibility, the black hole might have stunted star formation entirely, its radiation and jets clearing out the raw materials needed to birth new stars. Yet the real enigma is how NGC 1277 escaped the usual fate of galaxies. Over billions of years, even the quietest galaxies tend to absorb fresh gas or collide with neighbors, sparking new stellar life. But this one exists in perfect isolation, as if someone pressed pause on its evolution. Some astronomers speculate it's trapped in a cosmic desert, a region of space starved of intergalactic gas, leaving it stranded in time. Others wonder if its dark matter halo, the invisible scaffold shaping galaxies, is unusually sparse, preventing it from attracting new material. But here's the twist: relics like this might be more common than we thought. Recent surveys suggest the early universe was littered with compact, massive galaxies that burned out quickly. Most were likely torn apart or absorbed into larger structures, but NGC 1277 survived by chance, a lone holdout from a bygone cosmic era. Studying it is like unearthing a dinosaur bone, one that hints at a lost world where galaxies grew fast, feasted recklessly, and died young. NGC 1277 isn't just a curiosity, it's a challenge to our understanding of galactic life cycles. Why did it stop forming stars when others thrived? What silenced its engines so completely? Every answer we uncover peels back another layer of the universe's hidden history, proving that even in the vastness of space, some secrets stay locked away until we learn to ask the right questions. Moons aren't supposed to dwarf planets, at least that's what we thought until astronomers stumbled upon Kepler 1.625b's impossible companion. Orbiting a gas giant 8,000 light-years away, this candidate exomoon isn't just large, it's planet-sized, roughly the mass of Neptune. If confirmed, it would shatter every assumption about how moons form and what they're capable of. Picture Earth's moon, then imagine it swelling until it rivals Jupiter. That's the scale of this cosmic oddity, a moon so colossal it blurs the line between satellite and sibling. The discovery hinged on a telltale dip in starlight. When the planet Kepler 1.625b transited its star, the Hubble Space Telescope caught a second, fainter, dimming shortly after, like a shadow trailing a shadow. This tiny fluctuation hinted at something extraordinary, a moon massive enough to carve its own fingerprint into the light. Further analysis revealed even more strangeness. The planet and its moon orbit so far apart that their gravitational dance causes detectable wobbles in their transit timing, a celestial tango unlike anything in our solar system. What makes this system so revolutionary isn't just the moon's size. It's the challenge to our theories. Moons typically form in one of two ways, either coalescing from debris after a planetary collision like our moon, or getting captured by a planet's gravity like Neptune's moon Triton. But a Neptune-sized moon that defies both scenarios, a collision violent enough to spawn it would likely obliterate the planet, while capturing something so massive seems gravitationally improbable. Some scientists speculate this might be a binary planet system, two worlds born together with one dominating the other's orbit. Others wonder if it's a rogue planet snatched by Kepler 1.625b during a close encounter. Then there's the moon's potential atmosphere. A body this large could retain gases, raising the tantalizing possibility of clouds, weather, even habitable conditions, though the radiation from its host star would likely strip away any chance of life. Still, the mere existence of such a moon forces us to reconsider the diversity of planetary systems. If moons can grow this immense, what other extremes might be lurking in the cosmos? The debate isn't settled yet. Some researchers argue the data could be explained by stellar activity or instrument noise, and follow-up observations are scarce due to the system's distance. But whether this moon is confirmed or not, its possibility has already expanded our cosmic imagination. It's a reminder that the universe doesn't care about our textbooks. It thrives on the unexpected, crafting anomalies that force us to rethink the rules. And somewhere out there, among the infinite stars, another impossible moon might be waiting to challenge us all over again. Some stars refuse to die, at least not in the way we expect. When a massive star exhausts its fuel, it's supposed to go out in a blaze of glory, collapsing inward before exploding as a supernova, scattering its guts across the cosmos. But every now and then, the universe throws us a curveball, a star that cheats death, reanimating in a grotesque parody of its former self. Astronomers call these cosmic survivors zombie stars, and they're some of the most baffling, unpredictable objects in the universe. Take the case of SN 2014J, a supernova spotted in the galaxy M82. At first, it behaved like any other stellar explosion, brightening rapidly, then fading over weeks. But then, something strange happened. Instead of disappearing into obscurity, the supernova's afterglow flickered back to life months later, glowing irregularly as if powered by some unseen force. The leading theory, a zombie star at the heart of the chaos. When the original star exploded, it might have left behind a mangled remnant, a white dwarf or neutron star, that siphoned material from a companion, reigniting in violent outbursts. It's the celestial equivalent of a corpse twitching back to life, fueled by cosmic cannibalism. Then there's IPTF14HLS, a supernova that refused to fade. Most stellar explosions dim steadily, but this one pulsed erratically for years, its brightness surging and plunging like a heartbeat. Scientists suspect a magnetar, a highly magnetized neutron star formed in the explosion, its unimaginably strong magnetic field channeling energy back into the debris, creating a feedback loop of destruction and rebirth. These aren't just dead stars, they're undead, trapped in a limbo between existence and oblivion. What makes zombie stars so fascinating isn't just their defiance of the rules, it's what they reveal about the messy, unpredictable nature of stellar death. Supernova were supposed to be straightforward. A star dies, leaves behind a compact remnant, and that's that. But these cosmic anomalies suggest the process is far more chaotic, with stars sometimes partially exploding or leaving behind remnants that interact with their surroundings in bizarre, violent ways. And then there's the darkest twist of all. Some zombie stars might be ticking time bombs. Take white dwarfs that narrowly avoid total annihilation in a supernova. If they're in a binary system, they could slowly steal mass from their companion until they cross a critical threshold, reigniting fusion in their cores and exploding again. It's a scenario that defies logic, a star dying not once but multiple times, each resurrection more violent than the last. The universe has a cruel sense of irony. Just when we think we've mapped the life cycles of stars, these undead anomalies rise from the grave to prove us wrong. They're cosmic puzzles wrapped in enigmas, forcing us to question what we know about death, rebirth, and the strange physics that govern the afterlife of stars. And with every new discovery, one thing becomes clearer in the vast, cold expanse of space: even death isn't always the end. Dark matter is the universe's greatest ghost story, an invisible substance that outweighs all visible matter 5-1, yet refuses to show itself. But what if this elusive stuff isn't just floating aimlessly in space? What if it clumps together, collapses, and ignites into something even stranger, a star we can't see? That's the radical idea behind dark stars, hypothetical objects so bizarre they could rewrite the laws of astrophysics. Unlike ordinary stars, which shine by fusing hydrogen in their cores, dark stars would be powered by something far more exotic: the annihilation of dark matter particles. Imagine a celestial furnace where invisible matter collides and destroys itself, releasing enough energy to sustain a star for millions, maybe even billions of years. These cosmic phantoms wouldn't emit light, but their gravitational pull would betray their presence, warping space-time and bending the paths of nearby stars like a hidden lens. The theory hinges on a specific type of dark matter called weakly interacting massive particles, or WIMP. If these particles exist, they could accumulate in the dense cores of early galaxies, colliding just often enough to produce heat. Over time, that heat might prevent gas clouds from collapsing into normal stars, instead forming dark stars, puffy, diffuse giants hundreds of times wider than our Sun. They'd glow faintly in infrared, their warmth the only clue to their existence. But here's the twist: dark stars might not stay dark forever. As they consume their dark matter fuel, they could eventually collapse, triggering the formation of supermassive black holes. That could explain a long-standing mystery: how gargantuan black holes appeared so early in the universe's history. when there wasn't enough time for them to grow by conventional means. Dark stars might be the missing link, the cosmic seeds that planted the monsters lurking in galactic centers today. The hunt for these phantoms is already underway. Telescopes scour ancient regions of the universe, searching for odd infrared signatures that don't match any known star. Others look for gravitational lensing anomalies, places where unseen mass distorts background light in ways that defy explanation. So far, no definitive dark star has been found, but the search is far from over. What makes this hypothesis so electrifying isn't just the science, it's the audacity of the idea itself. Dark stars force us to confront the limits of our imagination. For centuries, we've studied the cosmos by observing light, but these objects remind us that the universe's greatest dramas might be playing out in the shadows. If they exist, they'd prove that dark matter isn't just a passive backdrop to cosmic evolution. It's an active player, shaping galaxies and birthing black holes in ways we're only beginning to fathom. And that's the heart of the mystery. Dark stars aren't just curiosities, they're windows into a hidden layer of reality where the rules of physics might bend in ways we've yet to discover. Whether they're confirmed or not, their very possibility stretches our understanding of what a star can be and hints at the untold secrets still lurking in the dark. Saturn's North Pole holds a secret so precise it looks like it was drawn by the hand of a cosmic architect, a massive, swirling hexagon wider than 2 Earths, its razor-sharp edges defying the chaos of planetary weather. Unlike the turbulent cyclones of Jupiter or the shapeless vortexes found elsewhere in the solar system, this 6-sided storm has raged for decades, possibly centuries, maintaining its geometric perfection against all odds. It's as if nature itself decided to carve a snowflake into the atmosphere of a gas giant, and no one knows why. The hexagon was first spotted by the Voyager missions in the 1980s, but it wasn't until Cassini arrived in 2004 that scientists grasped its sheer strangeness. Each side stretches nearly 14,000 kilometers, and the entire structure rotates with clockwork precision, completing one full turn roughly every 10 hours and 39 minutes, matching Saturn's own rotation. Inside its walls, winds scream at speeds over 300 kilometers per hour, yet the hexagon itself remains eerily stable, a polygon stamped into the clouds. What makes this anomaly so baffling is how it violates the basic rules of fluid dynamics. On Earth, storms are chaotic, asymmetrical, and short-lived. Even Jupiter's great red spot, though persistent, is an oval blob, not a geometric marvel. For a hexagon to form and endure, something must be counteracting the natural tendency of fluids to spiral into curves or dissolve into turbulence. Some scientists point to laboratory experiments where rotating fluids can produce transient polygons, but those shapes flicker in and out of existence. Saturn's hexagon, by contrast, is a permanent fixture, etched into the planet's atmosphere like a cosmic tattoo. One leading theory suggests the hexagon is a standing wave, a pattern created by differences in wind speeds at various latitudes, like ripples frozen in a fast-moving stream. If the jet stream at Saturn's North Pole has just the right properties, it could theoretically trap energy in a 6-sided pattern. Others speculate about deeper forces, like interactions between Saturn's atmosphere and its hidden interior. The planet's magnetic field, for instance, might play a role sculpting the storm into its unnatural shape. Then there's the wild card. Could there be something about Saturn's composition, layers of exotic gases or pressures, that allows for such precise symmetry? But the hexagon isn't just a static shape, it's a dynamic engine. Infrared images reveal a towering hotspot at its center, where temperatures spike unexpectedly, and smaller vortices dance along its edges like moons orbiting a planet. These features hint at complex energy transfers, a delicate balance of forces we've yet to decode. Even more intriguing, The hexagon changes color with Saturn's seasons, shifting from golden hues to deep blue as sunlight waxes and wanes over its 30-year orbit. What makes this structure so mesmerizing isn't just its defiance of physics, it's the lingering question of whether it's unique. If similar patterns exist elsewhere in the universe, hidden in the atmospheres of exoplanets or even deeper within gas giants, we've yet to find them. For now, Saturn's hexagon stands alone, a reminder that even in the vastness of space, nature can still surprise us with precision bordering on artistry. It's a storm that refuses to conform, a puzzle that dares us to rethink everything we know about planetary weather, and proof that some of the universe's greatest wonders are hiding in plain sight. At the fringes of our solar system, beyond the orbit of Neptune, something massive is stirring, an unseen force tugging at icy bodies, warping their paths into bizarre, clustered orbits. These distant objects don't behave as they should. Instead of scattering randomly, they swing around the sun in unison, as if choreographed by an invisible hand. The culprit, many astronomers believe it could be Planet 9, a hypothetical giant 5 to 10 times the mass of Earth, lurking in the frozen darkness where sunlight is barely a glimmer. The story begins with Sedna, a dwarf planet discovered in 2003 with an orbit so stretched and elongated it defied explanation. Then came more oddballs, Biden, Goblin, and a growing family of icy worlds, all tilted at similar angles, all swinging outward in the same direction. Statistically, the odds of this happening by chance are astronomically low. Something had to be herding them. Enter Konstantin Batygin and Mike Brown, the astronomers who crunched the numbers in 2016 and found a startling pattern. These orbits could only make sense if a massive planet far beyond Pluto was shepherding them with its gravity. But here's the catch: no one's ever seen it. Planet 9, if it exists, could orbit up to 20 times farther from the Sun than Neptune, making it incredibly faint. Detecting it would be like spotting a single candle flickering in a snowstorm from thousands of miles away. Yet its influence is undeniable. Simulations show that without such a planet, the orbits of these distant objects should be chaotic, not neatly aligned. It's as if we're tracking a ghost by the disturbances it leaves in its wake. What makes Planet 9 so tantalizing isn't just its potential existence, it's what it implies about our solar system's history. Where did it come from? Some theorize it was ejected during the chaotic early days of planetary formation, slingshot outward but never quite escaping the sun's grasp. Others suggest a wilder possibility, that it's a rogue planet captured from another star system long ago. If true, it would mean our cosmic neighborhood isn't entirely ours. We might share it with an interstellar wanderer. The hunt is on. Telescopes scour the skies, searching for the faintest glint of reflected sunlight. Every new discovery of a distant, oddly orbiting object tightens the noose around Planet 9's possible location. Yet skepticism remains. Could there be another explanation? Some propose a primordial black hole, no larger than a grapefruit but with the mass of a planet, warping space itself. Others wonder if the collective gravity of countless smaller objects could mimic a single massive one. Until we find it, or rule it out entirely, Planet 9 stands as one of the greatest detective stories in astronomy. It's a reminder that even in our own backyard, mysteries linger. The outer solar system isn't just empty space. It's a frontier hiding secrets that could rewrite our understanding of how planets form and move. And if Planet 9 is real, it won't just be another world, it'll be a testament to how much we still have left to discover, even in the places we thought we knew best. Just when we thought we'd mapped the boundaries of our solar system, the Voyager probe stumbled upon something unexpected, a cosmic fence at the edge of the neighborhood. As these intrepid spacecraft ventured beyond Pluto, their instruments picked up a sudden surge in cosmic radiation, as if they'd hit an invisible wall. Scientists call it the Galactic Barrier, a mysterious region where the sun's influence wanes and interstellar space begins, but not without one last puzzling phenomenon. This barrier isn't a physical structure, of course. It's more like a turbulent zone where two great forces collide. On one side, the solar wind, a stream of charged particles from the sun, pushes outward like an invisible shield. On the other, the interstellar medium, the thin soup of gas and radiation filling the galaxy, presses inward. Where they meet, something strange happens. Cosmic rays, high-energy particles from distant supernova and black holes pile up, creating a belt of intense radiation that the Voyagers had to pass through like ships navigating a celestial storm. What makes this discovery so intriguing is how it challenges our assumptions about the solar system's edge. For decades, we pictured the heliosphere, the bubble of the sun's influence, as a smooth transition, like a river merging into the ocean. Instead, the galactic barrier suggests a messy, dynamic boundary where forces we barely understand create a kind of cosmic no-man's land. Some researchers speculate magnetic fields play a key role, tangling and amplifying the incoming cosmic rays. Others wonder if there's an unseen structure in interstellar space, a ripple in the galaxy's magnetic field that funnels particles toward us. Then there's the timing. Voyager 2 crossed the barrier in 2018, but Voyager 1 had passed through years earlier, and their data didn't quite match. The barrier seemed thicker in one region, thinner in another, as if it breathes and shifts over time. That variability hints at something even more profound. The edge of our solar system isn't static. It pulses, warps, and reacts to the galaxy around it like a living membrane. The deeper mystery: this might not be unique to us. Every star in the Milky Way likely has its own version of a galactic barrier, a turbulent frontier where its stellar wind battles the interstellar void. Studying ours could unlock secrets about how stars interact with the galaxy at large, and how protected or exposed we truly are to the harsh radiation of deep space. For now, the Voyagers drift farther into the unknown, their signals growing fainter with each passing year. But their final gift from the edge, this strange, radiant barrier, reminds us that even in the quietest corners of space, there are forces at work we're only beginning to fathom. The solar system doesn't just end, it fights back, leaving us to wonder what other surprises lurk in the dark. There's something deeply unsettling about a star that simply disappears. Not with a bang, not with a brilliant supernova visible across galaxies, but with a silent, invisible collapse, as if the universe itself hit the delete button. Astronomers call these events failed supernova, and they're rewriting the rules of stellar death. Imagine a massive star 20 times heavier than our Sun, burning through its fuel over millions of years. Everything we know says it should end its life in a cataclysmic explosion, scattering heavy elements across space and leaving behind a glowing nebula or a neutron star. But sometimes these giants just vanish. No fireworks, no debris, just an eerie absence where a star once shone. The first clue came in 2008, when astronomers monitoring a distant red supergiant named N694141 watched in disbelief as it flickered out without a trace. One moment it was there, a stable, aging star. The next, its light winked out, leaving behind only the faint infrared glow of dust where a supernova's shockwave should have been. The explanation: the star likely imploded directly into a black hole, skipping the explosive finale entirely. It's like watching a building collapse inward in perfect silence, leaving no rubble behind, just a hole in the ground where it once stood. What makes these events so chilling is the physics behind them. Normally, when a massive star's core collapses, the outer layers rebound off the dense neutron star at its heart, creating a shockwave that rips the star apart in a supernova. But if the core is too massive, or if the star loses too much mass before death, that rebound might fail. The core collapses straight into a black hole, and the outer layers, instead of exploding outward, get sucked in like water down a drain. No light escapes, no warning, just nothing. The implications are staggering. If stars can vanish this way, we might be missing entire chapters in the story of stellar evolution. Supernovae are cosmic recycling plants, forging elements essential for life: carbon, oxygen, iron, and scattering them across the galaxy. But if some stars skip this step, collapsing silently into black holes, entire generations of heavy elements could be locked away forever, trapped in the abyss. It's a cosmic vanishing act with real consequences for how galaxies evolve and how the building blocks of life are distributed. Then there's the detective work. Without the flash of a supernova, how do we even find these ghosts? Astronomers hunt for missing stars by comparing old and new sky surveys, looking for once bright objects that have disappeared. Infrared telescopes play a key role, searching for the faint heat signatures of dust warmed by a star's final moments before it was swallowed. And sometimes, just sometimes, they catch the aftermath: a black hole's gravitational pull warping nearby gas, or a burst of neutrinos, the only particles slippery enough to escape the collapse. But the biggest question remains: why do some stars die silently while others go out with a bang? The answer might lie in rotation, magnetic fields, or even the star's chemical makeup. Some theorists suggest binary companions could play a role, stripping away a star's outer layers before collapse. Others wonder if these events are more common in certain galactic environments, regions with intense radiation or turbulent gas clouds. Every failed supernova we find is a clue, a puzzle piece in understanding the delicate balance between explosion and implosion. In the end, these silent collapses remind us how much we still don't know about the universe's most dramatic transformations. Stars are the engines of creation, their death seeding the cosmos with the stuff of planets and life. But when they choose to vanish without a trace, they leave behind more than just darkness. They leave us questioning the very rules we thought governed their existence. And in that uncertainty lies the thrill of discovery, the reminder that even the most familiar processes in the cosmos can still surprise us. At the edge of the observable universe, where time itself seems to fold backward, lies an impossible beacon, Euler's J1342+0928, a quasar so ancient it defies logic. This cosmic lighthouse, blazing with the brightness of 1 trillion suns, existed when the universe was a mere 690 million years old, a toddler by cosmic standards. Yet here it is, hosting a supermassive black hole weighing in at 800 million times the mass of our Sun. That's like finding a fully grown sequoia tree sprouting from a sapling's roots overnight. Quasars are already extreme objects, galactic cores powered by voracious black holes, so luminous they outshine entire galaxies. But Euler's J1342+0928 isn't just extreme. It's an outright rebellion against our understanding of cosmic evolution. According to conventional models, black holes this massive should take billions of years to form, slowly feasting on gas, dust, and the occasional unlucky star. Yet this one appeared almost fully formed, as if the universe cheated its own rules. How could something so colossal emerge so quickly after the Big Bang? One theory suggests these early black holes didn't grow gradually, they were born big. In the universe's chaotic infancy, direct collapse black holes might have formed when dense clouds of primordial gas collapsed under their own weight, skipping the star phase entirely. Imagine a cosmic shortcut where gravity bypassed the usual steps and went straight to crafting monsters. Another possibility: these black holes grew at breakneck speeds, gorging on the abundant gas of the early cosmos in a feeding frenzy unlike anything seen today. But even that raises questions. Such rapid growth should have released enough radiation to blow away nearby gas, starving the black hole before it reached such staggering sizes. Then there's the quasar's surroundings. Its light carries traces of iron and other heavy elements, which typically require multiple generations of stars to forge and scatter. That means stars were already living, dying, and seeding the cosmos with metals long before this quasar ignited, pushing back the timeline for star formation itself. It's a cosmic chicken and egg problem. Did the first stars pave the way for quasars, or did quasars somehow accelerate star birth in their vicinity? The discovery of Euler's J1342 plus 0928 didn't just add another record-breaking object to the books, it tore a hole in our models. Suddenly, the early universe looks far more dynamic, far more efficient at building giants than we ever imagined. And that raises an even deeper question. What else was happening in those shadowy first epochs that we've yet to uncover? Every time we push our telescopes further, the universe reveals another impossibility, another anomaly whispering that our theories are still just rough drafts. This quasar isn't just a relic, it's a challenge, a dare from the cosmos to rethink how black holes grow, how galaxies awaken, and how the darkness of the early universe gave way to light. And as we stare back at its 12-billion-year-old glow, one thing becomes clear: the universe's childhood was far wilder than we ever dreamed. Some corners of the universe don't just defy expectations, they seem to mock them. Take the cosmic cold spot, a sprawling region of space so unnaturally frigid it's like a frostbite scar on the face of the cosmos. Stretching nearly 2 billion light-years across, this mysterious void in the constellation Eridanus is colder than its surroundings by about 70 microkelvins, a tiny number on paper, but a glaring anomaly when mapped against the universe's otherwise uniform afterglow. It's as if someone left the cosmic freezer door ajar, and scientists are scrambling to figure out why. This isn't just a minor temperature fluctuation. The cold spot was first detected in 2013 by the Planck satellite, which mapped the cosmic microwave background, the faint echo of the Big Bang. According to standard cosmology, the early universe should have relatively even temperature variations, like the gentle ripples on a pond. But the cold spot is more like a sudden, gaping hole in that pond's surface. Statistically, there's only a 2% chance such a feature could arise naturally from random fluctuations. So what's really going on? One leading theory suggests the cold spot might be a supervoid, a vast, mostly empty region of space where the lack of galaxies and matter allows light passing through to lose energy, creating a cooling effect. But here's the catch: even the largest known supervoids can't fully account for the cold spot's extreme chill. The energy loss simply doesn't add up, leaving astronomers with a glaring mismatch between observation and theory. That's where things get wild. Some researchers propose the cold spot could be evidence of something far more radical, a collision with another universe. In the multiverse hypothesis, our cosmos might be one bubble in an infinite froth of parallel universes. If one of these bubbles brushed against ours in the distant past, the energy exchange could have left behind a bruise, a thermal imprint in the form of this colossal cold patch. It's a controversial idea, to be sure, but it's one of the few explanations bold enough to match the anomaly's scale. Yet the mystery deepens when you consider alternative explanations. Could the cold spot be the shadow of a cosmic defect, a crack in spacetime left over from the universe's fiery birth? Some theories suggest topological defects like cosmic strings or textures could create localized distortions in the fabric of reality, leaving behind temperature anomalies. Others wonder if our understanding of dark energy is incomplete, and this cold patch is a sign of its uneven influence across the cosmos. What makes the cold spot so compelling isn't just its existence, it's the way it forces us to question the very foundations of cosmology. If it's a supervoid, why doesn't it behave like other supervoids? If it's a multiverse signature, how do we test that without direct evidence? Every new observation seems to deepen the puzzle rather than solve it. Even the latest galaxy surveys, which map the distribution of matter in the cold spot's vicinity, offer conflicting clues. Some show a slight underdensity of galaxies, while others find nothing unusual at all. Perhaps the most haunting possibility is that the cold spot isn't just a curiosity, it's a warning. If our best models can't explain such a massive feature, what else might they be missing? The universe is under no obligation to conform to our equations, and anomalies like this remind us how much is still hidden in the shadows. Whether it's a bruise from a parallel cosmos or a flaw in the quantum tapestry of our own, the cold spot stands as one of the most tantalizing and humbling enigmas in modern astronomy. It's a cosmic Rorschach test, inviting us to stare into its depths and confront the limits of our understanding. And the more we look, the more it seems to whisper back, "You haven't seen anything yet." Black holes aren't supposed to be this small. At least that's what astronomers thought until they stumbled upon the unicorn, an enigmatic object so tiny, so lightweight, it defies the very definition of what a black hole should be. Tucked away in the constellation Monoceros, just 1,500 light-years from Earth, this cosmic oddball weighs in at just 3 times the mass of our Sun, making it one of the smallest black holes ever discovered. But here's the catch: it shouldn't exist. According to conventional astrophysics, when a massive star dies, it leaves behind one of 2 remnants. If it's moderately heavy, it collapses into a neutron star, a city-sized ball of ultra-dense matter so tightly packed that a single teaspoon would weigh 1 billion tons. If it's even more massive, it implodes into a black hole, an object so dense not even light can escape. But between these 2 extremes lies a ghostly gap, a theoretical no-man's land where no stellar corpses were thought to survive. The unicorn, with its measly 3 solar masses, sits squarely in that forbidden zone. So how did this cosmic misfit form? One possibility is that it started life as a neutron star, only to siphon extra mass from a companion star, pushing it over the edge into black hole territory. But the unicorn's companion, a red giant, shows no signs of violent theft, no erratic orbits or stripped layers. Another theory suggests it might be the remnant of an unusually lightweight star that somehow bypassed the neutron star phase entirely, collapsing straight into a black hole under exotic conditions we've yet to understand. Then there's the haunting question of how we even found it. Unlike its gargantuan cousins, which announce their presence with blazing accretion disks or gravitational waves, the unicorn is practically invisible. Astronomers detected it indirectly by watching its companion star stretch and warp as it orbits their shared center of mass. The star's light dims and brightens in a telltale rhythm, betraying the unicorn's gravitational pull, a cosmic dance where one partner is nothing but darkness. What makes this discovery so revolutionary isn't just the black hole's size, it's the implications. If the unicorn exists, there could be countless others lurking in the shadows, a hidden population of miniature black holes bridging the gap between neutron stars and their more monstrous relatives. Their existence would rewrite the rules of stellar evolution, forcing us to reconsider how stars live, die, and transform in their afterlife. And that's the real mystery here. The unicorn isn't just a curiosity, it's a key that might unlock new chapters in our understanding of cosmic extremes, proving once again that the universe doesn't care about our textbooks. It thrives on the exceptions, the outliers, the things we never saw coming. And somewhere out there in the silent dark, another unicorn might be waiting to challenge everything we think we know. We think we know what the universe is made of: stars, planets, gas, dust, the tangible stuff we call normal matter or baryonic matter. But here's the cosmic twist: about half of it is missing. Not hiding in black holes or tucked inside dark matter, but gone, vanishing from our inventories like a magician's trick. This is the missing baryon problem, and it's one of the most frustrating gaps in modern cosmology. The math is undeniable. By measuring the cosmic microwave background and the abundance of light elements forged in the Big Bang, scientists can calculate how much baryonic matter the universe should contain. Yet when they tally up all the visible galaxies, stars, and gas clouds, nearly half of that matter is unaccounted for. It's like balancing a checkbook and finding billions of dollars mysteriously absent with no paper trail. Where could it all be? One leading theory points to the cosmic web, the vast filamentary network of gas that stretches between galaxies. Most of this gas is so hot it's invisible to optical telescopes, glowing only in faint X-rays. But even accounting for this intergalactic plasma, the numbers still don't add up. Some researchers suspect the missing baryons might be lurking in even harder to detect forms. Ultra-diffuse clouds of warm gas, or perhaps exotic phases of matter that don't interact with light the way we expect. Imagine searching for a whisper in a hurricane. The signals are there, but drowned out by the universe's noise. Then there's the possibility we're simply looking in the wrong places. The missing matter could be concentrated in cosmic voids, those enormous, nearly empty regions between galaxy clusters. Or it might be tied up in faint, ghostly structures like dark galaxies, objects with plenty of mass but too few stars to spot. Some astronomers even speculate about primordial black holes, formed in the universe's first seconds, quietly hoarding baryons without emitting light. The hunt for these elusive particles isn't just academic. Baryonic matter is the raw material for everything we see: planets, life, even ourselves. If half of it is hiding in forms we can't detect, that changes our understanding of how galaxies form and evolve. It's like trying to bake a cake with only half the ingredients listed in the recipe. The results will never quite match expectations. New tools are finally shedding light on the mystery. Space telescopes like the European Space Agency's Athena mission, set to launch in the 2030s, will scan the skies for X-ray signatures of hidden gas. Other projects are mapping the subtle distortions in the cosmic microwave background caused by baryons drifting through space. Each clue brings us closer to solving the puzzle, but the universe isn't giving up its secrets easily. What makes the missing baryons so fascinating isn't just their absence, it's what their discovery would reveal about the fabric of the cosmos. They could be the invisible threads stitching the universe together, the hidden scaffolding behind the scenes. And until we find them, we're left with a humbling truth: even the ordinary matter in the universe is still full of surprises. There's a moment in every cosmic detective story where the evidence stops making sense. For astronomers studying the early universe, that moment came when they peered back over 13 billion years and found galaxies that shouldn't exist. These ancient cosmic cities, seen as they were just a few 100 million years after the Big Bang, aren't the fragile, infant structures we expected. Instead, they're colossal, fully formed, and brimming with mature stars, as if the universe hit fast forward on galactic evolution. Take GNZ 11, for instance. This galaxy, spotted by the Hubble Space Telescope, dates back to when the universe was a mere 400 million years old, a cosmic toddler. Yet it's already hundreds of times more massive than other galaxies from that era, packed with stars that had to form impossibly fast. Or consider the recent James Webb Space Telescope discoveries. Galaxies like CERS-1 and MACS1149JD1, which appear so massive and structured that they'd need star formation rates 100 times higher than anything seen in the modern universe to explain their size. It's like unearthing a skyscraper in the ruins of a Stone Age village, a glaring anachronism that rewrites history. The problem isn't just their size, it's their sophistication. These early galaxies aren't the messy, turbulent clumps predicted by models. They have rotating disks, spiral arms, and even central bulges, features that should take billions of years to develop. Some even host supermassive black holes far larger than expected, as if the seeds for these monsters were planted almost immediately after the Big Bang. The universe, it seems, skipped the awkward teenage phase entirely, presenting us with fully grown adults right out of the gate. So where did our models go wrong? One possibility is that star formation in the early universe was radically more efficient than we thought. Perhaps the pristine gas clouds of that era, unpolluted by heavy elements, collapsed into stars with near-perfect efficiency, birthing galaxies in a fraction of the time it takes today. Others speculate about exotic dark matter physics, maybe the invisible scaffolding of the cosmos clumped together faster in those early epochs, accelerating galaxy growth. Then there's the wild card. Could these galaxies be the descendants of even earlier structures, forming from pre-existing matter we've yet to detect? But the implications go deeper than just tweaking equations. If galaxies matured this quickly, it suggests the universe's dark ages, the murky period before the first stars ignited, might have been shorter and more dynamic than we imagined. It also raises existential questions about our place in cosmic history. If giant galaxies were already thriving when the universe was less than 5% of its current age, what does that say about the inevitability of cosmic structure? Are we living in a late, sluggish era of galaxy formation, watching the tail end of a process that peaked eons ago? Every new telescope that gazes deeper into the past seems to find more of these rule breakers, each one chipping away at our neat timelines of cosmic evolution. They're not just outliers, they're signposts pointing to chapters of the universe's story we've barely begun to read. And as we turn those pages, one thing becomes clear: the early universe wasn't just a simpler time. It was a forge operating under rules we're only starting to glimpse, rules that might still be written in the stars we see today. Dark energy was supposed to be constant, a steady, invisible force pushing the universe apart at an ever-increasing rate. But what if it's getting stronger? That's the terrifying possibility behind phantom dark energy, a theoretical twist that could rewrite the fate of the cosmos. Imagine a force that doesn't just accelerate the universe's expansion but grows more potent over time, like a car with a gas pedal stuck to the floor. If real, this phantom energy wouldn't just stretch space, it would eventually shred it, tearing galaxies, stars, and even atoms apart in a cataclysm cosmologists call the Big Rip. The discovery of dark energy in the late 1990s was shocking enough. By studying distant supernova, astronomers realized the universe wasn't just expanding. It was doing so faster and faster, as if some unseen repulsive force was overpowering gravity. The simplest explanation: a cosmological constant, a uniform energy woven into the fabric of space itself, never changing, never fading. But phantom energy throws that assumption out the window. Instead of remaining steady, its density could increase as the universe grows, making its push against gravity more vicious with every passing eon. Here's where it gets apocalyptic. In a Big Rip scenario, phantom energy's escalating strength would first pull galaxy clusters apart, then individual galaxies. Next, stars would be ripped from their orbits, followed by planets torn from their suns. In the final moments, the force would overcome the very bonds holding matter together, dismantling molecules, then atoms, then nucleons, until space-time itself fractures into meaningless foam. The entire universe, from the largest supercluster to the tiniest quark, would dissolve into chaotic, disconnected fragments. The evidence for this nightmare scenario is still sparse, but tantalizing clues exist. Some measurements of the universe's expansion rate show slight inconsistencies with the standard model of dark energy. Certain supernovae appear dimmer than expected, as if space is stretching faster in specific regions or epochs. Could these be hints that dark energy isn't constant after all? Or are they just cosmic noise, statistical flukes in an otherwise orderly cosmos? Even if phantom energy is real, the timeline is mind-bogglingly long. Current estimates suggest a Big Rip wouldn't occur for another 22 billion years long after our Sun has died and the Milky Way has merged with Andromeda. But the implications are immediate. If dark energy can evolve, then our understanding of fundamental physics is incomplete. The cosmological constant might not be so constant after all, and the fate of the universe could hinge on forces we're only beginning to imagine. What makes phantom energy so unnerving isn't just the doom it forecasts, it's the reminder of how little we truly grasp about the universe's underlying rules. Dark energy already accounts for 68% of the cosmos's energy budget, yet we don't know what it is. Is it a property of space, a new kind of field? Or something beyond our current physics entirely? Every anomaly, every deviation from the expected could be a clue, or a red herring in the greatest detective story of all time. For now, phantom energy remains a specter lurking in the equations, a what-if that challenges our assumptions, but in the vast darkness of the cosmos, where the unknown far outweighs the known, it's a reminder that the universe's final act might be far stranger than we've dared to dream. And whether it ends in a whisper, a crunch, or a rip, one thing is certain: the cosmos has never played by our rules. Saturn's rings are iconic, delicate bands of ice and dust that have mesmerized astronomers for centuries. But imagine a ring system so vast it makes Saturn's look like a mere speck in comparison. Enter J1407b, an exoplanet with rings so colossal they stretch over 200 times wider than Saturn's, spanning nearly 120 million kilometers, wide enough to swallow the distance between Earth and the Sun. If Saturn's rings are a bracelet, J1407b's are a cosmic hula hoop spinning around its host star in a display of celestial grandeur that defies explanation. The discovery of this ringed giant came in 2012, when astronomers noticed something bizarre in the light curve of its parent star. As the planet transited, the star's light didn't just dip smoothly, it flickered erratically, as if something with intricate structure was passing in front. Further analysis revealed the truth: not a single solid object, but a labyrinth of rings, complete with gaps and subdivisions, eclipsing the star in a complex dance of shadows. The scale is staggering. If you replaced Saturn with this system in our solar system, the rings would dominate the night sky, appearing larger than a full moon and visible even in broad daylight. But how does something so immense and intricate even form? Saturn's rings are thought to be the remnants of a shattered moon or captured debris, but J1407b's rings are on another level entirely. One theory suggests the planet might be a super Saturn, a gas giant surrounded by a sprawling disk of material left over from its formation. Over time, moons could have coalesced within this disk, their gravitational influence carving out the gaps we see, just as Saturn's moons sculpt its rings. Yet the sheer size of this system implies an environment far more dynamic than anything in our solar system. Then there's the question of stability. Rings this vast should dissipate over time, their particles colliding and scattering into space or clumping together into moons. The fact that they persist hints at unseen forces at work, perhaps shepherd moons hidden in the gaps, acting as cosmic gatekeepers to prevent the rings from spreading too thin. Or maybe the planet's magnetic field plays a role, channeling charged particles in ways that reinforce the ring structure. Without direct observation, these ideas remain speculative, but they paint a picture of a system where gravity, magnetism, and orbital mechanics intertwine in a delicate ballet. What makes J1407b even more intriguing is what it tells us about planetary diversity. Before its discovery, no one imagined ring systems could reach such extremes. Now, astronomers wonder if it's an outlier or just the first of many. Could there be other mega-ringed planets lurking in the cosmos, each with its own unique architecture? And what might their existence say about the formation of moons, planets, and even planetary systems as a whole? This exoplanet isn't just a curiosity, it's a challenge. A reminder that even the most familiar phenomena can take on breathtaking new forms when we look beyond our solar system. Its rings, shimmering silently in the darkness, are more than just debris. They're a testament to the universe's boundless creativity, urging us to rethink what's possible in the cosmic tapestry of worlds. And as we peer deeper into the unknown, who knows what other wonders and what other rings might be waiting to dazzle us? Most planets follow the rules. They orbit stars, basking in the warmth of a solar embrace. But not these cosmic rebels, drifting through the void, untethered to any sun. Rogue planets roam the galaxy like interstellar nomads shrouded in eternal night. Astronomers estimate there could be billions of these dark wanderers in the Milky Way alone, outnumbering stars by as much as 20 to 1. Some are ejected orphans, flung from their birth systems by gravitational chaos. Others may have formed in isolation, coalescing from cold, starless clouds of gas like failed stars that never ignited. Whatever their origins, they defy our most basic assumptions about what a planet should be. The first confirmed rogue planet, CFB DSIR 2149, was spotted in 2012, its faint infrared glow betraying its presence in the abyss. Since then, microlensing surveys where a planet's gravity briefly magnifies the light of a distant star have revealed dozens more, but the real surprise. Some of these worlds might not be the frozen wastelands we imagined. Take, for instance, SOFT IE2007. This Jupiter-sized rogue, discovered in 2020, emits a mysterious warmth, suggesting it could harbor active geology or even thick, heat-trapping atmospheres. If tidal forces or radioactive decay keep its core toasty, who's to say it couldn't host subsurface oceans like Jupiter's moon Europa? That raises the tantalizing possibility of life in the dark. Without a star to provide energy, rogue planets would rely on internal heat or chemical reactions to power potential ecosystems. Picture extremophile microbes thriving near hydrothermal vents in pitch-black seas, or atmospheres dense enough to trap geothermal warmth, creating pockets of liquid water. It's a haunting thought, entire biospheres evolving in complete isolation, cut off from the rest of the galaxy, their existence unknown until some lucky telescope catches a fleeting glimpse. But the biggest mystery remains their birth. Some rogues are clearly victims of cosmic violence ejected from young solar systems when gravitational tugs from sibling planets or passing stars sent them careening into the void. Computer simulations show this chaos was especially common in the early universe, when star clusters were crowded and unstable. Others, though, might have formed solo, collapsing directly from gas clouds too small to spark stellar fusion. These sub-brown dwarfs blur the line between planet and star, challenging our definitions. Then there's the ultimate question: could rogue planets ever find a home? Occasionally, one might plunge into a new star system, either captured by gravity or colliding with an existing planet. Some theorists even suggest that our own solar system could have stolen a rogue or two. Neptune's moon Triton, with its backward orbit, is a prime suspect. It's a reminder that in the cosmic dance of gravity, nothing is ever truly lost, just waiting to be reclaimed. Rogue planets are more than just celestial drifters. They're proof that the universe thrives on exceptions. In their darkness, they carry secrets about planetary formation, the limits of life, and the untold stories of systems that never were. And as our telescopes grow sharper, we're only beginning to glimpse the vast, hidden population of worlds that wander unseen, each one a silent testament to the galaxy's restless, unpredictable nature. Einstein's theory of relativity tells us gravity bends light, but witnessing it warp time itself. That's exactly what's happening with time-delayed quasars, cosmic lighthouses whose flickers arrive at Earth like echoes in a hall of mirrors. These brilliant beacons, powered by supermassive black holes, don't just shine steadily. Their light curves twist and repeat, as if the universe itself is hitting the rewind button. The reason: some photons take shortcuts through spacetime, while others loop around massive galaxies, arriving months or even years apart. It's relativity in action, written across the cosmos in delays we can measure. Take the famous double quasar SDSSJ100 4+4122. What looks like two distinct quasars is actually one. Its light split and bent by a foreground galaxy's gravity, creating twin images. But here's the twist: the images don't flicker in sync. One lags behind the other by 417 days, a delay caused by the longer path its light must travel around the galaxy's gravitational well. This isn't just a curiosity, it's a precision test of general relativity. By comparing the delay to the galaxy's mass, astronomers can verify if Einstein's equations hold true across cosmic distances, and so far they do with staggering accuracy. Yet some time-delayed quasars defy even these expectations. In 2018, researchers studying quasar QSO2237 plus 0305 spotted something bizarre. Its light echoes weren't just delayed, they were reversed, replaying brightening events backward like a film running in rewind. The likely culprit: a rare alignment where light loops around the black hole's accretion disk, flipping the signal sequence. It's as if spacetime itself becomes a funhouse mirror, distorting not just the path of light but the very order in which we see it. What makes these anomalies so invaluable isn't just their strangeness, it's their utility. Time-delayed quasars are cosmic stopwatches, letting us clock the expansion of the universe. By measuring delays across different wavelengths, astronomers can calculate the Hubble constant, the rate at which the cosmos grows. Discrepancies in these measurements might hint at new physics, perhaps flaws in relativity, or the influence of dark energy's evolution. But the grandest revelation lies in what these quasars teach us about black holes. The delays encode secrets about their feeding habits, revealing how matter spirals into oblivion. In some cases, the flickers match theoretical predictions of hotspots, clumps of plasma orbiting the black hole, their light stretched and duplicated by relativistic effects. It's like watching a cosmic ballet where gravity choreographs every step and the dancers are particles moving at near light speed. The universe doesn't just obey the rules, it shows them to us, writ large in the flickering glow of quasars. And with every delayed photon, every echoed flare, we're reminded that spacetime isn't a static stage but a dynamic, twisting fabric where light dances to gravity's tune. These anomalies aren't just quirks, they're masterclasses in the laws that shape reality and proof that even a century after Einstein, relativity still has surprises to reveal. From vanishing stars to invisible forces, these 28 cosmic anomalies are more than just scientific curiosities. They're humbling reminders of how much we still don't understand about the universe. Every time we think we've unraveled one mystery, another takes its place, each more bewildering than the last. Take Tabby's star, flickering erratically as if something vast is obscuring its light, or the Great Attractor, pulling thousands of galaxies toward an unseen cosmic heavyweight. These aren't just gaps in our knowledge, they're doorways to entirely new realms of physics waiting to be explored. What makes these discoveries so exhilarating isn't just their strangeness, it's how they redefine the boundaries of possibility. A century ago, black holes were dismissed as mathematical oddities. Now, we're debating whether dark stars powered by invisible matter might exist, or if phantom energy could one day tear spacetime apart. The universe constantly outsmarts us, revealing phenomena that defy textbooks and force us to rethink fundamental laws. And that's the beauty of it. Science isn't about having all the answers, but about asking better questions with each breakthrough. Technology plays a crucial role in this never-ending quest. The James Webb Space Telescope peers deeper into the past than ever before, uncovering galaxies that shouldn't exist so early in cosmic history. Gravitational wave detectors listen for ripples in spacetime, revealing collisions between black holes billions of years ago. Yet, for every puzzle solved, like confirming the existence of gravitational waves, dozens more emerge, like the enigma of rogue planets or the true nature of dark flow. The more we see, the clearer it becomes. The universe is a puzzle with pieces we're only beginning to recognize, but this isn't just a story for astronomers. These mysteries belong to all of us. They spark curiosity, fuel imagination, and remind us that wonder isn't reserved for textbooks. It's written across the night sky, waiting for anyone to look up and question. Whether it's a backyard stargazer spotting an unusual flicker or a researcher analyzing data from the edge of the observable universe, discovery is a shared journey. And with advancements in AI, citizen science, and international collaborations, the next groundbreaking revelation could come from anywhere or anyone. So what's next? Perhaps we'll finally detect dark matter directly, or stumble upon a celestial phenomenon so bizarre it rewrites physics. Maybe we'll find evidence of other dimensions or uncover the truth behind the wow signal. One thing's certain, the cosmos will keep surprising us. Every anomaly we solve will reveal deeper layers, stranger truths, and grander questions than we ever anticipated. And that's the real magic, not in knowing everything, but in knowing there's always more to learn. The universe isn't just vast, it's alive with mystery, constantly challenging us to see farther, dig deeper, and stay curious. Whether you're an avid astronomer or simply someone who gazes at the stars in awe, remember the greatest discoveries often start with a single question. So keep wondering, keep exploring, and most of all, keep looking up. The next cosmic revelation might be